Hey, I'm Courtney Waterman, your tutor. Lover of anime, manga, and math. And you just tuned into another session of Tutor Me Sempai.
Welcome back, everyone. Today we're jumping into a 12th grade topic, finding trig limits at a point. Now, if you're new to my channel, I'll be putting time codes for this video in the description box below, so use that to skip ahead to whatever part of the video you think is most interesting. As always, if you have any questions about what you see today, or even your own homework, you can always put in the comment box below, or visit my Facebook page at Tutor Me Sempai and tell me all about it there. At the end of this video, I'll be linking my 12th grade playlist, in which I cover a lot more topics. So if you're interested in that, make sure you stay tuned. This video is going to have 4 parts, so leave a like, smash subscribe, and let's get started! So today we're going to be jumping into finding your trig limits at a point. And to do that, we're going to focus on our basic trig functions. Your sines, cosines, tangents, etc. Now finding the limit for these functions is going to be very simple because these functions are going to be mainly continuous. Now I say mainly because they're not continuous everywhere. Tangent has asymptotes. Now sine, cosine doesn't, but tangent has asymptotes, which means that it's not going to be continuous everywhere. There's going to be some vertical asymptotes that break up the function, but your sine and cosine are going to be continuous everywhere. And early on this channel, we had a video that said continuous functions are going to have that special property of having its limit equal to its value at that point. So wherever your trig function is continuous, you're going to have the limit equal the value of that trig function. Hence, we're continuous. So if you're trying to find the limit of sine of x as x goes to 0, we know that sine is going to be continuous at 0. In fact, sine is continuous everywhere. So all you have to do is plug in 0. And sine of 0 is going to be 0. So the limit of sine of x as x goes to 0 is going to be 0. Cosine, if you're trying to find a limit as x goes to 0 of cosine now, then you're going to do the same thing because we know that cosine is continuous at 0. And when you plug that in, you get 1. So the limit of cosine x as x goes to 0 is going to equal 1. Now tangent is a little interesting because it has those asymptotes. However, at 0, there is no asymptote, it's continuous. So all you have to do is plug in 0. And now what's tangent of 0? Well, tangent of 0 is going to be 0. But if you didn't remember that, remember that your sine of 0 over cosine of 0 is what tangent of 0 equals. When you're trying to find your limit of trig functions, trig identities are going to play a huge role. Don't forget them. Don't try to wipe them out of your mind. They're going to be so useful for these, so make sure that you have them handy. Your trig identities. So tangent, if you didn't remember what that was, it's sine over cosine, and you're just plugging in your zeros everywhere, which this is going to equal 0. 0 over 1 is going to be 0. So when you're trying to find your limit of your trig function where it's continuous, all you have to do is plug in the value into your trig function and you'll get what the limit equals. So now that we've covered these basic trig functions, let's move on to our next section where we start setting up some fairly interesting shortcuts. So I call this section the setup because each of these 3 limits are going to be the building blocks for 3 shortcuts that we'll be talking about in our next section. However, we don't know what these limits are. So we need to find these limits before we can start setting up those shortcuts for us. And if you were to plug in your 0, you would notice that you're going to run into a problem very quickly. By plugging your zeros for all of these, you're going to get 0 over 0. This is going to be 1 minus 1 over 0, which is, once again, 0 over 0. And this is going to be 0 over 0. We have our indeterminate form. This is an issue. We don't have a limit now because this tells us we got work to do. However, we don't know which work we need to do because unlike earlier on this channel where we had some factoring that we could do when we had our indeterminate form, there's no easy factoring that we can see for these trig functions. So what do you do when you're not sure of how to find your limit? Well, go back to your basics, the basics of the basics. Plug in a bunch of points and see how the function behaves. What does the function approach when you're coming from the left and the right? Remember, when you're trying to find your limit, you have to find the left and the right hand limit and make sure they're approaching the same number. So do the same thing for each one of these. I'll start you off with the first one, but I'll give you what the limit is for these next two. So verify what they are on your own at home and make sure you're getting the same exact thing that I'm getting. So to make sure we're doing our left and right hand side, we'll be plugging in our negative 0.01, negative 0.001. We'll plug in our 001 and our 0, 1, and we're going to be seeing how this function is going to be behaving as we're approaching 0 from both sides. So let's say you had sine of 0.01 and you're dividing by 0.01. When you do that, what do you get? When you plug this into your calculator, what do you get? Now make sure your calculator is in radians, because if not, you may get something too far off. Make sure it's in radians. Plug this in and see what you get. Now, if you were to do this, you would see you get 0.999983, yada, yada, yada. This is really close to 1. So we're thinking just from the first one, maybe 1? We'll find out as we plug in the rest of these numbers. So we see when we have our 0.01, it looks like we're going to have 0.99983. So let's say we add an extra 0 in here. We now have 0.001. When you plug this into your calculator, what do you get? Well, this is going to give us 0.9999983. A few more 9s here. So write that up here. A few more 9s here, and it seems like it's getting closer and closer to what? 1. It's looking promising. However, we're only approaching from one side, the right-hand side. We have to approach from the left-hand side and make sure it's approaching the same exact number. So now we're going to make this negative, and we have to get rid of this. And when we do so, when we plug all of that into your calculator, what do you get now? In fact, this equals the very same thing. So I didn't even have to erase it. When you have your negative 0.001, you're going to have the same exact thing here. How about when you get rid of one of these zeros and now you're just dividing by 0.01 but negative? Well, this may look a bit familiar. Let's say we had that. We're going to have 0.999. Very familiar to what we had when it was positive, right? So we have 4 9s, a 3, and as we are approaching 0 from both the left and the right, it seems like it's getting closer and closer and closer to 1. So we know that our function seems to be approaching 1. Therefore, our limit should be 1 as x approaches 0. That's how you're going to find your limit when you're really not sure of how to go about it. Take some numbers on your left and your right hand side and make sure that your function is approaching the same number from both angles. So like I said, I want you to do the same thing for these, but I'm going to give you what their limit actually equals. So this is going to be 0. The limit of 1 minus cosine x all over x as x goes to 0 is going to be 0, while this one is going to be 1. The limit of tangent x over x as x goes to 0 is going to be 1. So these are going to be absolutely crucial when you're trying to set up your shortcuts. Either you commit these to memory or you commit to finding these every time, because by knowing this, you'll be able to quickly answer a bunch more trig limits. So let's jump into those shortcuts. This is going to be the first shortcut that we're going to be covering. The limit of sine of x over x as x goes to 0 equaling 1 means that the limit of sine of ax, a times x within your sine, all over bx, it doesn't have to be the same a, whatever that b is, it could be a different b, just make sure it's not 0, as x goes to 0 is going to be a over b. So as long as your b is not 0, this is going to be true. Your shortcut is going to be true. But why is this the case? Why is this shortcut true if you know that this is true? Well, let's find out. Let's say we had something like this. The limit as x goes to 0 of sine of x, well, instead of sine of x, sine of 5x over x we want to find that limit. Now we know based on this shortcut that this should be 5 over 1 or just 5. But let's see if we get 5 by utilizing what we know about this. So if this is true, we know that this should be 5. Well, let's do a little manipulation. This is going to be a lot of manipulation. That's pretty much what trig function or limits of trig functions are going to be. Manipulating. Either manipulating with your trig identities or manipulating with what I'm about to show you here. So when we have something like this, the first thing we want to do is try to get this looking similar to the setup of our shortcut. Now, this was sine x over x, right? Sine x over x. The constant in front of our x was the same. The constant in front of this x is not the same. So we want to get this looking very, very similar. So let's multiply top and bottom by 5. And that's going to get this looking the same. Now, we're doing this because we're multiplying by 1. We're not changing anything, but it does change the feel. We're not changing the value, we're changing the feel. So this is going to now be the limit as x goes to 0 of 5 times sine of 5x all over 5x. Now, you may be looking at this like this looks a lot more complicated. How is this a shortcut? I'm even more lost than when I first began. Well, let's say instead of this 5x, we make things simpler. Let's say we have this rule here. Y is going to equal 5x. So we rewrite this to look like this. The limit of 5 times sine of y all over y, as instead of x now, y goes to 0, because as x goes to 0, y is also going to 0, right? You see this, as x goes to 0, y is going to go to 0, so you can have as y goes to 0. We're substituting our y in for everywhere there's a 5x. So now this looks very similar to this. And you know that the limit of a constant is always going to be the constant. So you can break this up to be 5 times the limit of sine of y over y as y goes to 0. And we already said that this is true. Now this looks just like this. So we know this is going to be 5 times 1, which is just 5, right? This is why if we have this, the setup for this shortcut, this is automatically going to be true. A over B. If you know your shortcut, you don't even have to do any of this math. You just take the coefficient and put it over the coefficient here. A over B. That's the shortcut. Your setup gave you the shortcut, and now you can skip all of this unnecessary work unless you have to show your steps. And remember, all we did was try to make this look like this. So you're multiplying by your constant 1, right? But it looks a little different in order to make sure that we can have the same setup top and bottom. If there's a 5x here, you want a 5x here. If there's a 4x, you want a 4x. If there's a 10x, you want a 10x. And vice versa. If this was 20x and this was only 2x, we want to factor out to make sure that this looks like this. You can't put something into that sign, but you can manipulate the constants attached to this x very easily. So make sure that you are making this look like that so you can take advantage of this shortcut. So this is the first shortcut. Let's move on to our second shortcut. So this is going to be our second shortcut. Now this one may be even more obvious than the first one. And it's saying that if we know that the limit of 1 minus cosine x over x as x approaches 0 is going to be 0, then it doesn't really matter what your constants are attached to these x's. It's going to equal 0. The limit is always going to go to 0. So let's see it in action. Let's say you had the limit as x goes to 0 of 1 minus cosine 2x all over x. Now we're saying that this is going to be 0. But the first step we have to do is try to figure out why that's true. So let's multiply top and bottom by what to make it look like this. So we have a 2 inside. So we're going to multiply top and bottom by 2. And when we do that, let's actually rewrite this to give us a little bit more space. So it was the limit as x goes to 0 of 1 minus cosine of 2x over x. And we multiply top and bottom by 2. And that gives us the limit as x goes to 0 of 1 minus cosine of 2x times 2 over 2x. Now we know that we can do the same substitution, right? Let's say that y equals 2x. Let's rewrite this. We have the limit, and we know that y is going to go to 0 now, of 1 minus cosine y over y, and this top is multiplied by 2. And you know that your limits, you can break them out this way. The limit of, as y goes to 0, of 1 minus cosine y over y times the limit of 2 as y goes to 0. You're finding the limit of each part. This 2 can easily be rewritten as 2 over 1, breaking it up. So the limit of all of this is going to be the limit of this times the limit of this. That's what you got here. And we know that this is going to be 2. All of this goes to 2. However, this looks a lot like this now. What is the limit of this if this is always true? This goes to 0. That goes to 0. 0 times 2 is going to be 0. So it doesn't matter what this is always going to force it to 0. Let me rephrase that. It doesn't matter what this constant is, this is always going to force it to 0. So if you have a setup like this, and you have A's and B's, it doesn't matter if they're the same or not. If you have A's and B's, it looks just like this. You can easily say, without doing any work, that this limit is going to be 0. Let's jump into our last shortcut for today. So this is going to be our last shortcut for today. And it says that if we know that the limit as x goes to 0 of tangent x over x equals 1, then that means that we are guaranteed to have the limit of tangent of ax over bx as x goes to 0. It has to be a over b, as long as b is not 0. Now, b doesn't have to be a, it could be a, but it can't be 0. And if this is true, then you're going to have a over b. Now, this looks very similar to our sine shortcut, and you'll see why this plays out the same way. Let's say we had this limit here. The limit as x goes to 0 of tangent of 6x over 2x. Now, this is saying that this should be 6 over 2 or just 3. Keep that in the back of your mind. Let's make sure we're getting that. But the first thing we want to do is try to make this look like that, because we want this to look like this. So what do we have to multiply top and bottom by in order to make this look like that? This is going to be top and bottom by 3 here, right? 3. And by doing so, we'll have the limit as x goes to 0 of tangent of 6x times 3 over 6x. And this is going to be the same exact step. We're going to have y equals 6x. And then we're going to substitute in. When we do that, we have the limit as y goes to 0 of tangent of y times, let's put 3 tangent of y all over y. And we can always write this as the limit as y goes to 0 of 3 times the limit as y goes to 0 of tan y over y. This is going to go to 3 because it's a constant. It's a constant. And this we know to be 1. 3 times 1 is going to be 3. So we know that this follows the same rules as our other two shortcuts. We don't have to do any of this work as long as we know this to be true. If your setup is true, then what follows has to be true. As long as it follows this appearance, your answer is going to be A over B. And the main thing you want to do to start off is make sure this looks like this. Now, for all three of our examples, we had you multiply top and bottom by something, but that's not always the case. So I'll give you one more quick bonus one for this shortcut, and it's going to be true for the other ones as well. But let's say we have the limit as x goes to 0 of tangent of x over, let's say, 4x. Now, there's nothing that we can multiply top and bottom by to make these equal, but what we can do is just factor out that 4 here, right? Now, we can actually break this up to be the limit as x goes to 0 of 1 over 4, right, times tan x over x. You can do that. In this case, you don't have to multiply top and bottom by anything. You're just factoring out because this had no constant bigger than 1, so you're going to make sure that this has nothing bigger than 1 attached to it. Take out everything else you need, and then just separate them out like you were doing before. This is going to be the limit as x goes to 0 of 1 over 4 times the limit as x goes to 0 of tan x over x. This is going to be what? That goes to 1/4 because it's a constant. This goes to 0 because, sorry, not 0, 1. It goes to 1 because of our setup. That means we have 1/4 times 1, which just gives you 1/4. But once again, you don't even need to do this because you have your shortcut, which tells you it should have been A over B. A was 1, B was 4, thus your 1/4. Now, I want to leave you with a warning. It is very important that you stick to the shortcuts. Now, these 3 shortcuts are going to help you, but there are plenty other patterns and other shortcuts that you will find and you can take advantage of as you're doing these trig limits. However, it's important that you stick to the shortcuts that you have and you don't stray from them. Don't force something to fit into a shortcut that is not supposed to fit. Now, what do I mean by that? Well, let's say we had a question like this. The limit as x goes to 0 of 1 minus cosine of, let's say, 2x all over x squared. This looks very similar to this. However, it's not the same thing as this. This has an x squared. This doesn't have an x squared here. And you may think, well, okay, that's fine. What if I just factor out one of the x's, right? So I can easily rewrite this as the limit as x goes to 0 of 1 over x times 1 minus cosine of 2x all over x, right? I can do something like this and then break up our limits, right? However, this is going to go to what? This is going to go to infinity. This is going to go to 0. Infinity times 0 is not always infinity and is not always 0. You can have something else. This is not going to help you. You got to do a little something else here. So don't try to fit in to your shortcut something that wasn't supposed to be there in the first place. You're going to have to use other methods of attacking this besides this shortcut. This shortcut does not apply for something like this. In this case, you want to use something like your trig identities. This is screaming trig identity here. So if you were to, let's say, factor out a -1 here, so let's say a -1, you have your cosine of 2x minus 1 now over x squared. Then this right here is a trig identity you can take advantage of. So let's rewrite it with its trig identity substituted in. We're going to have -1 times what's cosine 2x minus 1. Well, this is going to be a -2 sine squared x. Taking advantage of our trig identity, we can plug this in, and now we have an x squared in the bottom, which means that now we can get rid of that negative there. So we just have our 2 sine squared x over x squared. Well, now we can actually break this apart. you can break this into 3 different limits. Believe it or not, 3 different limits. So let's start there. Let's say we have the limit as x goes to 0 of 2 sine squared x over x squared. This is going to be the limit as x goes to 0 of 2 times sine x over x times sine x over x. Think back to your shortcut. See, we started somewhere else, right? We started with something that looked like this, but not quite that. And now we're utilizing our other shortcut, because what does this go to? What does this go to? These go to 1, which means that your final answer is going to be 2 times 1 times 1, which equals 2. If you were to look at this example here, remember our original example was x goes to 0 of 1 minus cosine of 2x over x squared, and say, oh, that looks very similar to this. This is going to be 0. You would be wrong. That doesn't equal 0. It equals 2. My warning to you is, don't try to fit in something into your shortcut that doesn't fit. Utilize a shortcut, but utilize it for what it's meant for. So I hope you were able to follow along with today's video, and I hope you now know how you can find your trig limits at a point. However, if you have any questions about what you saw today, or even your own homework, you can always put in the comment box below, or visit my Facebook page at Tutor Me Sempai and tell me all about it there. If you hadn't done so already, remember to leave that like. It surely helps the channel by letting YouTube know that you found a video helpful. And if you found a video helpful, so can someone else. So leave a like, hit the notification bell, smash the subscribe button, and share the video with a friend. Well, that's all the time I have for today. I'm really hoping this helped with your homework. I'm looking forward to seeing you again next week. I'm Courtney, here's your playlist, and this has been another session of Tutor Me Sempai.